Hello and welcome to the College of Engineering poster competition. We are just about to get started. Testing, testing, 1, 2, 3. Testing, testing, 1, 2, 3. Sounds like we're ready. Let's go ahead and get started with our first poster here, the Whittier Slide Zone Avalanche Mitigation.
Thank you very much. So, we'll give a brief overview of our project here. We are trying to knock down these massive avalanches that form on this hillside, dubbed Slide Zone F7. Which is, if you're driving towards Whittier, it's right before Portage Lake. There's a little elbow tunnel that you go through.
All right, here. We're going, but yeah, we're gonna get a little bit closer to you with the camera. Okay. Your mic's not working very well. Go ahead.
Okay. All right. Perfect. We're just going with the camera.
We're just gonna go with the camera.
Sounds good. As I was saying, our project aims at preventatively mitigating these massive slides from generating these derailing slides that can come and knock trains off the railroad and potentially cross DOT facilities as well. So we're looking at a replacement to the current mitigation strategy, which is essentially shooting a massive World War II cannon at the side of this hillside. We're looking at a replacement for the next coming years, and we have evaluated 4 different alternatives, one being drone delivery, second being Daisy Bell, helicopter sling, third being snow shed, and finally our preferred alternative, which are these mounted remote avalanche control towers. You can see a cost breakdown. We're about in the $2 million range for this entire project, and yeah, that's our project.
All right, thank you so much. All right. Okay, who wants to give me an overview of your poster here?
I can do the overview.
Yay!
So is it recording?
It is.
Okay. Can we start whenever?
Yeah.
Okay, well this is the Funny River boat launch facility. We're trying to build a boat launch in the Funny River community near the Kenai River, off the Kenai River in Soldotna. We looked at a couple different alternatives based on the Kenai River, and we determined that this location would be the best fit for a boat launch based on the hydrological data. I also forgot to mention that a big committee used a couple different site plans, and they determined that this plot of land was the best fit for that based on all the data given. And then we had 3 different alternatives for our boat launch facility. We have alternative 1, which is a little bit of a bigger site plan. It has 30 truck and trailer parking and 30 passenger parking. And it's pulled through, makes it a little bit easier, but it is a bigger square foot area, a little bit more, uses a little bit more land than we would need. This costs about like $1.2 million based on all the different factors. And then we have our second alternative, which is a little bit smaller than that, but it has backup parking. But we think it's a lot better if you would want to develop it in the future. Develop this land in the future, have a park, do anything. Right now this is just a boat launch facility. And this is 1.2 million, or 1.1 million, sorry. So we decided that this alternative would be the best fit based on cost, cost, what we need to use, and for future development. So.
Awesome. So you prefer alternative too?
Yeah, we prefer alternative too. Just based on, cost is a big factor into that. Boat Launch 1 is a little bit better, just for the area and usability of parking. But Boat Launch 2 is just, if you want to develop it in the future, it's a lot less invasive to the land, and you develop it better. And then this is the actual boat ramp profile.
Awesome. Well, thank you so much.
No worries.
Okay. Who can tell us about this poster?
I'll try.
All right.
The background noise is still a little loud, but it's
Okay.
Just go.
Yeah, go on ahead.
So this is the AMATS Fireweed Lane Rehabilitation Project. The main reason why this project is coming into play is it is overbuilt for motorized users. And so what we want to do is reconfigure the typical section of the lane width to accommodate more for the active transportation users, so the pedestrians traveling the corridor. So as you can see here, we have minimal space for people to travel along the corridor. And so the main mission here is that we propose a typical section that will reconfigure, like I said, reconfigure the widths to better accommodate for the 3 user groups, considering that it's overbuilt for motorized users. And so that's what we did here. The 3 user groups are transportation users, motorized users, and property owners. So we considered it, we did a matrix, we did the analysis, and what we came up with is that the 3-lane typical section best accommodated for those 3 user groups as equally and as fairly as possible. So that's kind of the gist of our presentation.
All right. So I see on your matrix there that providing snow storage is something that you accomplish in the 2-lane system and kind of accomplish in the 3-lane system. Can you tell us what that means?
Yeah. So for the 2-lane, it just allows for more space to be able to use for snow storage, considering we have larger sidewalks, we have larger on-street bike lanes, so in the winter we're not going to be using that, so it allows for more space. The 3-lane, it doesn't allow for as much space compared to the 2-lane, so for that reason it gets the yellow box.
Awesome. Yeah. Well, thank you very much.
Yeah, thank you.
Get started.
So basically we have a large language model, or LLM, running locally on whatever computer. Initially, we were using this Raspberry Pi, so everything was running just on this. But as you can see in some of our response times, some of them get up into the 3-minute range, and that's kind of too long for a user to talk to the machine and then wait for a response. So we kind of upgraded to the computer, but we could also upgrade this if we just paid more money to get a better GPU to get those response times down. But all these models do work just on this. But right now we have a client-server architecture. So when the user talks to the machine, it will translate that to text, send that to the server, and then the server will send the response back to the client, and then output that as speech. So basically, you just talk to it, and it'll talk back.
Nice, very nice. What did you find the biggest challenge on your project here? Oh, come closer. So the camera's mic is pretty weak.
Probably hardware limitations.
Okay.
We didn't really want to spend like $500-600 on a nice GPU, so we that's why we developed the client server architecture in the first place, because we couldn't do it on a on a Raspberry Pi CPU.
Yeah. You
Like,
needed more compute, right?
way more.
Yeah.
And even now on the M1 Max, which is pretty good, it's still like not perfect, but
Awesome.
Yeah.
Well, thank you very much.
The difference in response time from this to there is like going from a couple minutes to a couple seconds.
That's great.
So yeah.
Like 60 times faster, right? At least. Awesome. Thank you so much.
Okay, so we designed an interactive web map. It's on a website. Basically what it is we're targeting the Dena'ina homeland, and on this map we have different locations of different places that are culturally significant to the Dena'ina people. So like right here you can see like we have a lot of places in Anchorage. It includes like Kincaid Park, Point Warrenzoff, Eklutna. And when you tap on a pin, it's pretty simple to use. You just tap on it, it brings up a title, description. We have like a local description, which is just like for people who aren't familiar with these places, because there's people that live in Alaska, there's people that don't live in Alaska.
Right.
So it just helps people familiarize the place. And then just like the main chunk of it is like the place name story. It just details some piece of Dena'ina history or culture, because that's really what we want to highlight. And we also have like a photo gallery, just like introducing people the photos and the images
of that area,
yeah,
right?
just so people can get like a nice visualization.
Yeah.
And one really cool part of this app is we collaborate with not only our clients but also their clients' clients. That is, we got actual like Dena'ina people to speak the language. So it's also like an educational app where if you want to learn how to pronounce the Lishla, you can play the audio and it'll play it to you. It'll play the audio pronunciation. So it's really cool. We also have audio narration, so like storytelling. This is actually a Dena'ina culture told by Peter Kalifornsky that showcases a lot of the Dena'ina clans, and we got someone to record that narration, which pronounces all the Dena'ina names. It's really cool. It was a very big collaborative effort and a very big Dena'ina community effort, which is what we want to obviously emphasize and highlight.
That's very cool.
These are a lot of the people that worked with us too. As you can see, we have a lot of the audio recordings. A lot of people helped work on this project.
Yeah, I was going to ask, what were your main sources of information about all of these locations?
It was we worked with Dr. Maria Williams and Jessica Ross. They helped to provide a lot of information. A lot of these people also, Danita Slauson, I believe she went over. We had like a document that showcased what we wanted to put for each location, and so we got like direct feedback from the Dena'ina people to put in these locations.
Awesome. Well, thank you so much.
Of course.
All right, go ahead.
Okay, great. Well, so what Jared and I did is we did a machine learning for hardware classification project. So I'm currently interning at GCI, so I have the opportunity, I have the privilege of going through all these sites, specifically with United Utilities Incorporated. They were acquired about GCI about a decade ago. A lot of equipment that is not accounted for, a lot of equipment that was kind of haphazardly accounted for. Just a problem when you acquire a large company that has lots of different sites, has lots of different equipment. Where is this stuff? This stuff, it says it's here, It's not there. It's in a different rack somewhere else, right?
Yep.
So the idea was to kind of streamline the process that I was doing, which was to manually go through the pictures, scroll through them, try to find this equipment, and then try to flag down an engineer and be like, hey, I found it, it's here, can you add it to the database, etc. So, it's just extraordinarily tedious.
Yeah, labor intensive.
Yeah, and very labor intensive. So let's have a computer do it.
Yeah.
So the idea is to use a convolutional neural network. This was something that I had a class for, a computer vision class last semester, and I already built out kind of a model so I knew how it worked. So I kind of took that knowledge and I made it even more extensive and attached to this project. Instead of using a custom-built convolutional neural network like I had before, I use transfer learning because it's better.
Yeah.
Because I'm trying to apply this to a real-world problem. I don't want to use kind of the sophomore code that I wrote in class.
Right.
I want to use, hey,
something a little more robust.
Exactly.
Yeah.
Smarter people have done this better. I'm going to take from them.
Yeah.
So I applied. We used Efficiency Net, which had pretty great results. Unfortunately, this is from a couple weeks back. So right now our F1 scores are way better. These metrics have come together beautifully. I have a 87% accuracy. I have a 85% F1 score. Super happy with the training model. And right now, we're still waiting for I still need some higher level approvals to run it on bigger training sets because I'd like to expand this out to the whole company.
Yeah.
But right now, what I'm dealing with is getting out log files. I used a heat map to find the equipment in the racks and really detail what it is, so that instead of me snipping pictures out of everything, I get a nice big file filled with all these pictures, where all this equipment is, and I'm just like, here's the thing.
Nice.
Here's all the equipment, all the stuff's ready to be modeled. Here's exactly where it is. Here's the site where it is, and this is it. This is the picture of it actually in the rack. So I'm really happy with how it turned out.
Have you seen any of that equipment migrate, as you've been trying to catalog it?
I'm sorry?
Have you seen any of that equipment move when you were trying to catalog it?
Not move somebody went.
Someone went and moved it from one room to another room in the same building.
Well, because I've been running it on. Because the data's from lots of different site years.
Yeah.
You'll see that. You'll just see stuff
hopping around.
Yeah, hopping around. And it's just, I understand why there's so much. A lot of the management is so frustrated with a lot of the RF technicians. But I understand with the RF technician. A lot of times it's hey, something went down. In the middle of nowhere, you're flying me out there. On a moment's notice, and I'm just trying to get the service back up and running.
Yep.
So, there's this, I understand where both sides are coming from.
Yeah.
And it's extremely tedious because every time an RF technician might change something and they need to update the databases, well, that's somebody else who does that, right?
Yeah.
So they're not doing it directly. So there's a lot of, I understand why this problem exists. But I don't think it's intractable. I think it's a good step towards making it a little more streamlined.
Yeah. How long would it take you to basically reevaluate the heat map for the entire company?
For every site?
For let's say one site.
For one site?
Yeah.
Not long at all.
A day or two? Or?
Yeah, most of the information's pretty good.
Okay.
So you're really just looking for the outliers.
Right. And you said to 87% accuracy or so, right?
Yeah, 87%. So I try to make it so it did a little bit of overfitting.
Yeah.
Which means it's getting more false positives, which is okay. Because if it's wrong and somebody's looking at it, they'll be like, that's wrong.
Yeah, they're not going to find it.
Yeah, they won't. Yeah, they're like, if somebody has the picture, they're looking at it, and they're like, okay, this is wrong, and you can discount that. So I wanted to make sure it was a little more on that end. Not too much, but it is. There's definitely stuff that it's gonna miss still.
Yeah.
It's not perfect, but it's definitely gonna cut down a lot of man-hours.
Awesome. What did you find most surprising about the process?
Simply just how complex it could be, and just working with GCI and getting into that atmosphere
Yeah.
and learning the process and approvals to just get everything going.
Yeah.
That was the
Who to talk to and at what point in the process.
There's a ton of bureaucracy.
Yeah, I believe
I
it.
was having meetings every other week with a new team, a new department, trying to get approvals for something I had no idea would need approved.
All right.
So for the security team, the lawyers, from the technicians who work on the stuff to the engineers who manage the databases. I mean, I had to get I couldn't believe how many hoops I had to jump through.
Lots of different, yeah.
So that was a big learning process. Was like just the amount of bureaucracy that exists in a large organization.
Awesome. Well, thank you so much. This is really cool.
Thank you.
Yeah.
Thanks for.
Go for it.
Okay, so in this project, we're working with a company called Denali Dreams. They're a soap company here in Anchorage, Alaska. And currently, to make their own soap bars, they use these plastic liners in PVC pipe tubes. And they came to us and they wanted us to find a solution to remove these plastic liners for environmental reasons.
Yeah.
And so we had to find how much force it would take to push that soap out without the plastic liner. So we measured it to be around 340 pound force. Yeah, they also told us they wanted to scale it to 20 inches of soap. So currently they're using 11 inches of soap. So we had to calculate that out, and it was around 660 pound force. But we applied a factor safety of around 1.5 just in case we wanted to make sure it would get any check. So it looked something like this, and then after we brought this design to the client, we found out that we can't use aluminum because it's corrosive to sodium hydroxide, and they use that for making soap, the soap process. So we had to redesign it with stainless steel, which is the one over there.
Okay.
We designed a system that would also ensure user safety, and so it requires two buttons. So you have to push two buttons at the same time to make sure no hands or anything gets inside in between that. We also designed it so that these plates can move back and forth, so they can use both the 11-inch tubes and the 20-inch. It also has a rubber sheet that will clean the inside of the tubes to make it a little bit easier for them. We found that this system would take approximately 3 seconds to push the entire tube of soap out and extract all the way, so it would save them a lot of time in the future.
Oh, yeah. Did you have any estimate how long this device would last? Like how many repetitions, how many cycles?
We estimate that it would have a infinite life cycle.
Oh wow!
But there are areas where it could potentially fail in the future due to manufacturing reasons, like this. Between that bolt over there and the edge of the base plate, it's a little bit thin, so they could add reinforcement in the future to make that last longer. But everything else was built to last. Also, not just for safety, but basically, yeah.
That's great. Well, thank you so much. Very cool project. All right, now we have our next poster, Arctic Truck 6x6 optimized steering design. So, what can you tell me about your project?
Yeah, we're working with Arctic Trucks. They're seeking certification with the DNR to operate their 6x6 vehicle in the Alaska tundra during the summers. One of the main concerns that DNR had was that a six-wheeled vehicle would have significant wear on the tundra. So DNR suggested that they add rear steering to both rear axles, but due to cost restrictions and optimization of funding for these custom vehicles, we really want to just add this one steering axle to the very rear to try and optimize. And so we went through a couple different case scenarios, looking at different options and looking at the effects of each scenario on ground wear. And we really focused on the Ackerman analysis method, the Ackerman factor, which basically means that the axes created by each wheel as it turns should all intersect at a common point, making all the wheels concentric to one another.
The purpose of that Ackerman steering is to ensure that the wheels are causing as minimal ground effects as possible. Those effects can't be removed completely, but the closer each wheel matches its ideal turning angle while the vehicle makes a turn, the more minimized the effects on the ground would be. So in case one, in red, we showed the effects we studied how closely the vehicle in its current design, how closely it matches its ideal Ackerman steering design. And using that as a base point to go off of, we moved on to our case two, where we added rear wheel steering to the vehicle by essentially taking the steering angles of the current front steering axle and just mirroring it on the rearmost axle. We reevaluated how closely the overall steering matched the ideals and found that despite the goal wanting to minimize the ground effects by adding this rear wheel steering, the overall effect just by replacing that rear axle would have probably been to cause a increase in the overall ground wear. So in our third case in green, that was where we optimized the steering mechanism designs as much as possible within the constraints of the vehicle's design and what is physically possible to make the wheels match their ideal angles as possible, so that the Ackerman factor, which is a measure of how closely the vehicle matches its ideal Ackerman steering angles, was as high as possible for both sets of steering axles.
All right, so in the green, are you reducing costs and reducing ground wear?
Overall costs of the vehicle would be going up by adding the rear wheel steering and further changing it by the optimizations.
Okay.
But while cost can be prohibitive, the overall desire was to make this vehicle suitable for operations in the tundra, which it currently is not rated for due to the concerns of the ground effects it would cause.
Okay.
The tundra is so fragile to any type of heavy vehicle operation that the essentially twisting of the rear axles led to too much. There was too much concern about how the effects that it would cause, and so by adding the rear wheel steering, it's hoped that the effects will be mitigated enough to the point that the vehicle could be certified for use out there for all sorts of different operations.
Awesome. Well, thank you so much.
Thank you.
Yeah, really interesting project.
Perfect.
All right.
Our project is looking at a type of renewable energy based off of energy from the tides, which is pretty promising, but right now it's too expensive to be pretty feasible, which is why we're going to make it more efficient. There's not much data on how we do that. So our project looks on blade geometry and how we can maximize the energy capture from tidal fuel. So the iterative approach between computer modeling using CFD and experimental testing. Our first iteration, we tested things like blade count and pitch angle, figured out which one was the best, moved on to test it both in the Flume and in the computer models, figured out which one was better. Then we moved up to our second iteration, where we tested 14 more blades, looked at things like blade width, we added hydrofoils, we tapered them, we made them wider, we did all, changed blades from 2 through 6, tested all of them only in the computer, and then we made our third iteration a combination of all the best attributes from all the blades in our previous iterations. Produced 3 blades, printed them off, and so we tested them in the computer and the experimental models. And we have our final results here. So you can see our number one blade was the 5 blade with the wide twist blade. They're outperforming every other blade by about 2%. And we'll see we have quite a bit of agreement between our computational blade performance and our experimental blade performance, with the difference of our top blade only being about 3 to 5%, which is pretty validating our two-method approach between CFDs and experimental data. And so moving forward, like I said, there's not much information on this, and so we're hoping someone can use our work to advance the tidal turbine energy industry. Obviously, we only did geometry. You can look at materials, bearing work, how your gearbox is going to be. There's much more to be done in this project, but we're just kind of getting a foot in the door of our blade performance designs based on our geometry.
Awesome. Do you have a sense of how they compare to one another, these 3 models that you developed structurally? Like how much wear and tear they can actually take?
We did no structural testing, primarily because we're only looking at our 3D tested material, which is by no means what it's actually going to be made of in the real world.
Ideally, what do you think it ought to be made of?
I would imagine aluminum with a lot of coating.
There's a lot of material properties that you're going to have to look at before putting something in a body of water, especially the ocean, just with all the sediment in it. So there's tons of stuff that you're going to have to consider before even thinking of putting this in the ocean.
Had you considered like sacrificial zinc or something like that to keep it from corroding?
We actually haven't really thought about any of that. We're really only focused on the geometry in this project, but I think definitely that's something to look at in the future.
Awesome. Well, thank you so much for your project.
Right, so our SEER design project, at the start of the semester, our advisor provides us a basic vibration magnetic absorber design. What this does is this passively absorbs vibration from the system via a free-floating magnet that's opposed by the rest of the 9 to the 7. And this can be attached to mostly vehicles such as aircraft and boats. And our goal for the project was to try to validate the data provided by a computer simulation of Capstone that was generated by our advisor at the start of the semester.
All right, yeah, go ahead and Awesome, thank you.
So basically, this is our final setup, and this is how we were able to actually run the test. So we ended up getting a conclusion with this graph. So this one right here, the one with the curves, is actually the software data. As you can see, it's pretty equal. It's at 0 at equilibrium. Unfortunately, our trials were very linear, which is not what we expected. We do take into account that the COMSOL data, it's in a way, the data is suggested to have like perfect conditions. So there's no real world things like vibrations and all this and that. So because of our linearity, we ended up running some tests to basically figure out why.
Come on now.
So, to discover possible errors that we were having, we ran some SOLIDWORKS FEA testing or finite element analysis testing on our result and found out that the displacement of our load cell was actually one of the biggest factors. And the other error with the SOLIDWORKS FEA that we did was this is best case scenario where the 3D printed products would be a solid instead of having 20% infill like about a 3D printed material. Our biggest displacement from the SolidWorks analysis was that we found out that the load cell was actually displacing around 0.27 millimeters, but to also find an exact real-life result, we did an actual testing in the lab to see the displacement of the load cell itself, and we found out that it was actually displacing about 1.77 millimeters, about 6 times higher than what we wanted. This also cancels out one of the assumptions that we had previously when conducting this lab of saying that the displacement of the load cell was negligible.
All right, very cool. So I'm guessing if you had to develop a new prototype, how would it be different?
So basically, so for the purposes of our experiment, we used what's known as a cantilever load cell, which is sort of like if you can imagine a bridge, and as the force is put on the end of that load cell, there's a slight deflection which a sensor reads out to the rest of our system, or the computer we use. Now, for future designs, we proposed using an inline load cell. How that works is basically we would align it, if you can imagine this as a load cell, align it with our sensor. As we move things around, this will be directly connected and just output the force without deflecting, which will affect that deflection, as Peter mentioned, is what sort of affects our data.
Okay, and that would that also have a linear pattern to it, or?
We hypothesized that data would look more like the COMSOL data, which is sort of decaying third-degree polynomial.
Very cool. All right, well, thank you very much.
Thank you.
Functioning fitness. Our clients did some market research. They found that, as people age, they stop doing everyday things around the house. They lose the ability to do those things around the house. So our app is just sort of
Oh, come closer, come closer.
our app just used to encourage the elderly to do everyday chores and stay active. That way, they stay mobile, they stay healthy, and just better quality of life.
All right. So, did you? I see that you're talking about the user interface here. Did you do studies with some of these elderly folk to see what they found easier to use, or?
So we didn't do any studies. Our clients themselves were our testers. And
Okay. So they're your beta testers.
Exactly.
Was there anything interesting that you didn't expect that you got for feedback?
Not that I can think currently.
Okay. And how effective was the app at actually getting people to, kind of get more engaged physically?
They're still testing it.
Still testing it?
Yeah, we don't have any hard metrics for you right now.
Okay.
Yeah, this is a prototype, but it does show as far, but it just kind of gets the baseline of what they are aiming for. Minimalistic UI, catered towards older people, and then for our back end, we use periodic syncing, so you can use the app locally, or you can use it off of Wi-Fi as well. But since we code it in both Android and iOS, Apple has powerful tools with their health app that you can also link with this to further track their fitness and stuff like that.
Oh, that's awesome. And I love the fact that you can have it, either on a server or not, depending on your preference. That's very cool. All right. Well, thank you so much.
Yeah, thank you.
Good job. All right.
All right. So our project was evaluating data encoding techniques for power-constrained embedded systems in remote areas. Alaska is very unique in the sense that there's not a lot of power out in remote areas and there's limited accessibility. A lot of these systems that we reviewed and looked at were battery powered with embedded chips that have limited memory and limited compression or limited CPU usage, as well as their main source of power from the battery is recharged by solar panels. This creates a unique problem when we're trying to find ways to have cost savings in both transmission power and storage on the device. We got with Beaded Stream and came to, got some temperature data samples from them to use for, because they're primarily the user of the embedded systems in remote areas. So we got our sample data from them. We got a 31 sensor temperature string with 5-minute incremental temperature readings over an hour. Gave us 744 kilobytes of data. So we originally went through and looked at a series of compression algorithms from zlib to C-standard, and then Huffman. Huffman was found to be the basis of all the code, all the algorithms, with additional compression techniques added on the other ones. But we found that they had a relatively similar compression ratio with the data pool we had. So we focused on just the Huffman by itself, based on its robustness and its compact size, and giving still great compression technique of lossless data. The way that the Huffman algorithm works is it takes and looks at the data pool and looks at the frequency of characters that are within the data, and takes the most frequent occurring character and designates it as a single bit or a limited bit. So you could have a 16-bit character and it'll store it actually as 1 bit. So you're having a 15 times savings in a 1 bit alone. From there, it creates a tree. As you can see here, where like A would be occurs very frequency in the data set, and it stores as a 1 or a 0, a single bit. B occurs the second most frequent, so it stores it as 3 bits, and so on. This creates substantial savings. We found with this technique, combined with another encoding technique, we found that a 744 kilobyte data pool could be shrunk to 240 kilobytes, giving us a 3 times savings on compression.
Yeah. So another compression algorithm that we looked into is actually called bit packing. So it's a very simple algorithm that it restricts the amount of bits that you need to use to actually store a number. So for example, an example temperature would be negative 2.34. How we're actually storing that as an integer is just multiplying it by 100. And that gives negative 234. As a 16-bit integer, we have this binary string here. The bits labeled in red are actually not needed. It's a negative number, so the leading bits are 1s. But with only 9 bits, we can correctly store that number and recover it at the end, lossless. So the 2 compression algorithms that we analyzed are Huffman and bit packing, and these are lossless techniques. So onto actually Iridium SPD transmission. So it actually uses a lot of power. So this graph right here is actually a power over time. So the total energy to use is actually 13 joules, while actually running these compression algorithms on a microcontroller or a CPU, it's in the range of millijoules. So by compressing that data, you're actually shrinking the amount of packets you need. So there's actually 2 budgets, one being the energy budget and the cost of transmission budget. So per kilobyte, it's actually $1.36, which is extremely a lot. So an example of lossless compression, an application of that in a remote sensor system is actually, taking photographs. So this is an example of a snow probe measurement. Over here we have the raw uncompressed image and the compressed image. They look very similar, but actually with this image we got a 93% reduction in the amount of data needed to store it. So actually transmitting images over Iridium, that's a lot of data, but with raw sensors, you're talking about less than a kilobyte, right? So onto results.
Yeah, so overall, we were pretty happy for this 31 sensor data set. We saw, a reduction close to 30 cents in overall cost savings. Going back to the energy budget, this definitely saves you energy when you compress it. Now, what he was going over earlier about the energy cost to send each packet, right? So if you have 340 bytes that you're sending, and you only need 1 packet to send that, you're not going to save as much energy just with 1 packet versus if you needed 3 packets to send data. And then we were able to get a compression ratio of 3. Now you only need to send 1 packet. You're going to save money, and you're also going to save energy. And again, this was for this 31 sensor data set. And then pretty impressive results for the compression as well. So this data set, we're pretty happy with the results in this.
Awesome. So talking about the compression overhead, was there a big difference in how much power was consumed using Huffman versus bit packing compression?
So this figure right here is actually just the power measurement of one packet being transmitted. So the region that I labeled overhead, that's actually when that Iridium modem is finding the satellite.
Oh, okay.
So the frequency
that's
band,
something else, yeah.
Yeah, the band that this Iridium modem transmits in, it was actually monitored with a software-defined radio. So the region labeled overhead was when it wasn't transmitting. I assume what's happening is it's actually trying to find a suitable satellite to transmit to. And in the transmission section, it's a lot shorter in time, but that's actually when I see activity on the frequency band.
Okay, so to restate the question in a different way then, is there a power difference in the different kinds of compression, how much power it uses?
Yeah, so that is kind of according to how much compression ratio you get. So the limit for Iridium packets, the 340 bytes.
Yeah.
So if you have a large data set, say multiple kilobytes,
right,
and you can shrink that, that means you need to transmit less packets. But the problem is with small data sets, if you're not filling up that whole packet, say you only need to transmit 100 bytes, you're still going to spend the same amount of energy to actually transmit that. So the data size, with regards to energy usage, the impact is by transmitting less packets.
Well, the question is, does using the Huffman compression differ in power consumption from using the bit packing compression?
It does, and we looked at that originally, but the amount of power needed to run the algorithm on the Huffman, on the data set we had, and we had a synthetic data stream up to 100 sensors, or 2.9 kilobytes. It was on the orders of picojoules and microjoules.
Oh, okay.
And same with bit packing was on microjoules. So it was insurmountable compared to the transmission costs and power usage. So we actually excluded it.
Yeah, okay. So it was just kind of negligible, right?
Yeah.
Negligible difference.
Yeah.
Cool. And what surprised you the most about your findings in the project?
Well, one thing that is surprising, so this is kind of inspired by what they're doing over there at BetaStream, a local company here in Anchorage. They're not actually compressing the data. They're sending a 2-byte, 16-bit number for each temperature. So actually, these results are promising, in the way that they can save transmission costs. And actually apply
a lot of money
compression to that, raw temperature sensor data set.
Yeah, awesome. Well, great. Thank you so much. Really interesting project.
Thank you.
So this is our project called Ballot Vision. The Division of Elections puts out the federally certified cast vote records, CVRs, and you can download them off the Division of Elections website. They come in a raw JSON format, so not very digestible, not very understandable, and they're very large enough that sometimes you can't even open the entire applications. They have 55,000 rows of formatted data. So what we did is we took those CVR files and we created a parsing algorithm that actually put them into a database so that we could start querying all of that data. And then we created a front end that created the user interface so that you could actually query the data and see what was on those ballots. So there's a lot of information. Some of it we're just like, we're not quite sure what that means, but it might mean something. We have an interactive map where you can click on districts or precincts and get information that way. We also have a summary page that we're continuing to develop with also charts and maps to give you a visual representation of that data. And we're continuing to expand. As we optimize the database, our queries become optimized as well.
Awesome.
Yeah.
That's really great work. So who are your biggest users, do you think? Like who's the most interested in using it?
We talked to some in the beginning, But the more users that we can get to actually go to the website and give us feedback, because what we may think is interesting may not be interesting to somebody else. And what we want to do is create a accessible point for everybody who wants to see what kind of data are you interested in. Well, we can do that.
Yeah, very cool. And so is this just local ballots, or is this, ballots from other states?
No, just Alaska's, and this one's specifically for the 2024 election.
Okay.
So there is data available for the 2022. Ranked choice voting, of course, was voted in 2020.
Right.
So we chose to focus on the 2024, mainly because there was a presidential one. And
it's interesting. Yeah. Awesome.
And this is all mostly federal and state, not municipality. Municipalities deal with their own data.
Yeah.
So.
Well, that's very cool. Thank you so much. Yeah, great project.
So, UAA is retiring its course evaluation tool idea. College of Engineering wants to create a new course evaluation surveys to replace it. These surveys are better designed to tailor questions to the specific needs of the course and to gather more meaningful feedback. The main problem with these surveys is that they are generally either too generic or too specific. Questions that are meant for all courses don't provide equally meaningful feedback, but then some questions that are too specific to a course do not provide or diminish the quality of responses that you will accept. Another issue that we have here is that surveys are generally too long. IDEA had approximately 50 questions or so, and suffer from the same generic and specific question format. So what we want to do here is that we have a custom question set that is applied to that specific course by the faculty. It is edited and modified by the faculty for that specific course's needs. And here we have our systems. We have our Django backend that is dealing with all the MySQL case queries, and the front end that everybody and the users will interact with. That is essentially our project. It's meant to provide faculty with more data that they can use to better refine their course. Because in the long term, is that when you get more meaningful feedback, you will improve your courses for your future students and also their experiences with you.
Okay, and so you convinced the chancellor, and they're going to use your product now, right?
We're going to certainly try.
Is it actually fleshed out enough to start using campus-wide, or?
Currently, this model, its functionality is near perform, or I would say it's functioning pretty well for the back end. However, our main focus wasn't the front end, which is what people will be interacting with. So it's a lot of mock-ups. Okay. So I would say give it another semester or two, and I think it would be fully fleshed out, fully tested.
Awesome. Very cool. What do you think was the most surprising thing that you ran across in your project?
So one of our requirements and constraints was that student ID or student confidentiality had to be preserved. Essentially, anonymous or no student IDs or tracking information could be associated with students' answers, and we needed to ensure that the system was in a secure place before they logged in. The biggest issue that we had was implementing Google authentication, which is essentially signing in with your Alaska.edu account.
Yeah.
Because when you do so, you get added benefits of multi-factor authentication, such as Duo.
Right.
That was our biggest issue when we came across this, and it actually led to the bottlenecking of development. Because without Google authentication, we could not connect the front end and the back end. That's what scared us the most.
Yeah.
However, at the end, we did get it working. We did get a nice working prototype up, and yeah.
That's awesome. Yeah, that's a major achievement. Well, good job. Thank you so much.
Thank you.
All right, and that concludes the live stream for today.